You can hear me, right? Okay. Thanks for coming despite having a busy schedule. So today, I will most importantly focus on these two papers. Not all qubits are created equal, and software mitigation of crosstalks and mixed computers. So in the previous presentation, we have seen several discussion about theoretical aspects of quantum computing, several algorithms like the Grover's algorithm, the quantum Fourier transform, and SVM. Uh, like so, today I would like to mainly focus on engineering aspect of quantum computers, quantum computing. It's more like just making this quantum algorithms work on like actual devices. So, so the contents will be mainly on the background, some discussion about like a general overview of executing quantum programs on quantum computer and like the variable aware qubit mapping. It's mostly focusing on uh, like running a certain quantum algorithms on a certain device. And like we see about the design for a variable aware qubit mapping and variable aware qubit allocation. Then finally, uh, about the instruction scheduling for to mitigate this kind of crosstalk errors, which is based on the second paper I showed. So let's start let me start my presentation. So generally, if we see the workflow of a gate-based quantum computer.
Oh, here.
Yeah.
So I think you're sharing different screen than your Zoom.
Oh.
So we cannot see your.
Okay, you can ask my screen.
No, we can see your screen changing.
Okay.
Screen.
Okay, but not on Zoom. Okay, what's the problem then?
Maybe try to share it again.
Oh, share it again. Okay.
And maybe try to share the presentation slide.
Okay. Yeah, I think I shared the presentation slide, right?
No, it's not.
Oh, okay. Yeah, sure. It was the desktop. How about now?
Yeah, it's synced.
It's working?
Yeah, but it's not still presentation.
Oh, it's not present. Okay. Sorry for the. Okay. This is the presentation slide, right?
No, you should focus on desktop too because that's the screen
Okay.
we share. Where is this? Oh, okay. You can see the slide. Oh.
They can see the slide?
You have to see this screen.
Yeah.
I guess.
I see. This would be better, I guess.
Yeah. Okay. I see the problem.
Yes. Okay. It's working right now. Perfect. So, okay. Okay. We're at this page, right? This page, right? Okay. So yeah, like this is the general workflow of gate-based quantum computers. We have, for example, if you have a problem, like you might be solving the traveling salesman problem. So we write a quantum algorithm for that. And there will be a description of this quantum algorithm with a circuit-based model, like just the given circuit. So we have the quantum processors. It might be of different architecture. So like here at compiler, like the compiler is going to translate this, like the language of circuit representation into like the physical thing. So although we might have very noisy and like a hardware with problem, this compiler could like some sort of research could be done like on how to like map this quantum circuit into the actual hardware and make the best out of like base like the base side of the quantum hardware. So like, for example, let's see specifically like IBM quantum processors. For example, if we see here, like we might have a quantum program that is like that requires application of single qubit gate and 2-qubit gate. So we might not be able to apply 2-qubit gate due to like the sparse connectivity of the hardware. For example, if we see this is like kind of through time, the IBM processors, like they previously they had a lot of connectivity among the qubits, but it could be one like disadvantage because like this connectivity has its own disadvantage in the performance of the hardware. So like if we see through time, it's becoming more sparse. So if we want to apply a 2-qubit operation from this qubit to this qubit, we might need to swap the information and to make them closer to each other to apply this 2-qubit gates. So like not all qubits are physically connected. So we need to bring the information closer together to apply 2-qubit operation. And where like IBM systems, they have a fixed frequency of qubit. Like having, if we apply 2-qubit gates in parallel, like there could be some collision of frequencies and it gives rise to some sort of error. So in order to avoid that scenario, like we have a sparse connectivity of qubits. So this, like in order to move the information on the qubit, like there's a qubit movement, like the compiler, like we have like a certain quantum compiler, it translates the ideal quantum program into physical qubit, into the physical definition, like into the physical state, using this swap gates to it insert them like randomly at every position. So yeah, like if we have here, we can see here we can see qubit 1 and qubit 3. If we want to apply a 2-qubit operation on this, there could be several passes, and like yeah, we have to bring this Q1 into C by swapping the information. Then we can apply 2-qubit operation from C to F. And this like case could be avoided by the compiler because it requires like many number of swap gates to bring the information like to qubits that are physically connected. So what this paper like proposed is, so like generally existing policies of this compiling, they only just focus on reducing the number of swaps. But like since all links and qubits, they don't have the same error rate and like they don't have the same link strengths, we need also to care about the strengths of this link. So like they proposed a variable aware qubit movement and allocation. So what this is going to do is like, let's imagine this hypothetical like 5-qubit quantum computer, and we want to apply a 2-qubit operation on those 2-qubit operation on Q1 and Q3. So either like there are two ways of moving the information on qubit A. The first one is to bring it to like here to D and then applying the 2-qubit operation. The second one is to move like the information on qubit A to B, then apply the 2-qubit operation. So if we see the number of swap, this pass has like large number of swaps. We like the pass is like longer, but this one is shorter. But since these links are stronger, we need to like when the compiler is doing this kind of translating this quantum program into like the physical into the physical case, it should take this pass because like it also has like lower amount of error. So this is the main idea of this variation aware mapping. So like they used a new metric to like to evaluate the performance of like the performance of the like this compiler. So what the like the metric was called PST, probability successful trial. It kind of evaluates the performance by dividing the successful trial to the total number of trials. So this is like the how they evaluated like the reliability of that hardware, that device. So like how do we design for variation-aware qubit movement? So the way it's designed is, first we have qubits, and we represent them as a node and a graph, the weighted graph, and then there will be an age, like so that age has a weight, and the weight is represented by failure rate of the links. So yeah, so after representing this, we compute a distance matrix. A distance matrix is, this distance matrix is finds like between two pair of qubits in the whole topology of like the backend. They will be, it calculates the shortest distance, or like the shortest number of swap, not swapped, but the cost here is since the failure rate. So we compute a distance matrix that that holds the information about the minimum cost of swapping two qubits that are located in different locations. Then the next step is to compute the node strengths of each qubit. So each qubit could be limited, like it could be connected with different qubits. So this node strength is calculated by the summation of the neighboring links, which is the weight. So if it is connected with qubits with like, and the link is strong, this node strength will be higher. So we need this quantity for qubit allocation later. So the next step is to break the input circuit into the layers uh, of like into a layers of different circuits. So if we have a certain quantum program, so these layers are like gates that could be applied in parallel. So those like we have a certain combination of single and two qubit gates. So this I0 represents a layer that uh, could be applied in parallel. So the fourth step is to find a qubit to physical qubit map. So if we have several different layers, what we need to do is to apply the second layer, we need to place the qubits next to each other so that we can apply the two qubit gates. So we need to find a set of swap gates that kind of translate this layer at m minus at i's layer of this given layer to the next layer. So yeah, this fourth step is going to do that. So finally, we find the optimal set of this swap operation that transforms the map in mi to mi plus 1. So since we already have the distance matrix here, we can use the Escher algorithm to find the like the optimal set of swap operations. So this one is like heuristic. So although we have an exponentially scaling search space, we can like it won't be difficult to solve. So for the qubit allocation, we have this algorithm. Yeah, just this one is to find like not all qubits, they don't have the same like node strengths, so that this allocation policy like chooses those qubits which has like higher or stronger node strengths. So yeah, like this is just like the algorithm will choose k nodes from the total connectivity of the backend with a good aggregate value. So yeah, this is the result they get from the simulation. Yeah, by the way, if you have any question in the middle, you can stop me and ask. Okay, so this is the result they get from this kind of uh, variable qubit movement and variable qubit allocation mapping. So this one is the baseline. The baseline tries to only minimize the number of swap operations, but these, like the yellow and the green one, they kind of also consider the variation of this link strength, whether it's strong or like weak link, so that they showed that if we map our quantum program onto a physical hardware by considering the link variation, we can get some sort of improvement in the like execution of our program and like the performance. So yeah, it has some limitation. So the limitation of this one is it uses a simplified error model, and it also ignores, it only try to reduce the number of swap operation, and it's like it doesn't consider much about the coherence error, which is like, even though like this type of qubit routing, uh, it could choose like a qubit route that has like so like many number of swap gates. So at this point, coherence error could be dominant. So since it didn't took this one into consideration, and the like the error model is kind of like a simplified version, this is one of its limitation. And it doesn't also consider some like other type of error and relation. So this is one of its limitation. So the second paper, like, which is software mitigation of crosstalks on noisy intermediate scale quantum computer, it tried to address like this type of error. So yeah, like what is a crosstalk? Crosstalk is actually if we want to apply two qubit operations in parallel, like there will be interaction between those two. Like, so when we apply two qubit operation, we have two qubits. So we just put those two qubits in resonance, so that like, yeah, we kind of we will be able to create some interaction. But if we are applying two qubit gates in parallel, like there will be a collision in frequencies, and also there will be some interaction between those two qubit gates. So we call this phenomena as a crosstalk, and it's the major source of error in NISQ devices. So in order to minimize this crosstalk, there are some hardware solutions. One is device connectivity design. So if you have a sparse connectivity of qubits, so we can avoid this crosstalk. And qubit frequency tuning. This is also like, if there is no any collision of frequency, then this is also like could be one way of like avoiding crosstalk and coupler tuning. But without going too much into the experimental, going too much into the experiment, we can do some sort of uh, like we can at least try to mitigate this crosstalk at a compiler level, or like at the software level. So that's what this paper is doing. So first, what they did in this paper is characterization of crosstalks. They, like, in order to characterize this crosstalk, they applied two qubit gates in parallel at the same time, and they measured the conditional error rates, and also applied like a single qubit alone, and kind of measured the like only single qubit operations, their error rate. And the solution they proposed was this. So like if we assume this one as a like just the 5 qubit quantum computer, and two could be a qubit that has lower decoherence time. So which means we need to apply the first gate and the last gate near to each other so that like the information on qubit 2 doesn't like lose its information. So we have this representation of the gate. Uh, like yeah, if we this is kind of like our quantum circuit, and if we try to apply these gates in parallel, like there will be a crosstalk between those two operations because we're applying them simultaneously. So in order to avoid this like crosstalk, we serialize these operations. For example, like if we insert barrier here, since those two operations are not applied in parallel, like there won't be any crosstalk here. So, but the problem is we see that qubit 2 has a low decoherence time, and we applying this gate like for a long time. So the information might lose. So there's a trade-off between decoherence and crosstalk. So what they did in this paper is to design an intelligent scheduler that avoids both problems. So for example, if we put this barrier here, like the decoherence time is like here low, and there won't be any crosstalk too. So this is an intelligence scheduler that kind of solves this trade-off. So like this intelligent scheduler, like this instruction scheduling detail is like this. We have a set of qubits and like GB a set of gates in our instruction. So we have these three variables: the start time, the gate duration, and the gate error rate. And there's also data dependency constraints, which means we cannot always parallelize an instruction because if you're applying like the information on one qubit could be important for the next instruction. So this cannot happen always. So there is also a data dependency constraint. So it's defined by the following equation, which means if Gj is gate J is greater than Gi, which means Gj depends on the like Gj should be executed next to like Gi, like those are gates, two qubit gates. So we kind of represent it with this equation. This is the start time plus the gate duration. So this is the constraint for data dependencies and gate error constraint. So for every gate Gj, we can have like a can overlap. This is a can overlap set, uh, like, and we define a variable which is called like overlap indicator. So this variable is what it shows is like if both instructions are not dependent on each other, then like this is going to indicate that both instructions could overlap. So so these are like the constraints that shows the gate error rate. For example, this one shows if like if we have three gates, G1, G2, and G3, if G1 is not overlapping with G2 and G1 is not overlapping with G3, so G1, like the gate error rate of like G2 is G1 is not overlapping with G2 and it's not overlapping with G3. So yeah, the gate overlap of G2 is here. Once. Let me, I think I have typo here. Yeah, like on anyway, yeah, this relationship like shows we can determine if those two gates are not overlapping, we represent them with the single error of like since they could not overlap, the gate error rate of this gate is determined by like its single gate error. And if it overlapped, if O1 is overlap, gate 1 is overlapping with 2, but not overlapping with 3. So the gate error rate of 2 is determined by the conditional error rate. So this constraint is to determine this set, like the overlapping set in our optimization. Like this instruction scheduling is done through an SMT optimization. constraint, like the coherence error here. Like this is the last gate, the start time of the last gate, and this is the start time of the first gate. So like by calculating this time difference, we can like quantify the coherence error like variable like this. And finally, we have the objective function. The objective function is to find is to minimize this state, which is composed of the like the gate error and the decoherence error. So in order to make it linear equation, since this one is like has some sort of exponential, and we can now solve that. Like in order to solve that with SMT optimization, we need to linearize this equation. So we took they took the logarithm of this equation and finally got the following objective function. So yeah, this is the result they got through serialized scheduling and parallelized scheduling. This is the Xtalk scheduling is like an intelligent scheduler or like the instruction scheduling that uses both parallel and serial scheduling and gives a better result we can see here. So that's all. Like if we see the overview of how this is done, we have a programming instruction, like which is our quantum circuit written in like a low level form, and there will be hardware mapping and routing. So in order to execute that quantum circuit on the hardware, we can use some sort of mapping and like qubit routing. Then like since we have a problem of decoherence and crosstalk, this could be like handled with this module proposed by this paper. Like it's a crosstalk adaptive scheduler, and we need some sort of characterization from the QC system in order to use this module. So this is like the overall like execution of the program. So that's it. Thank you. If you have any question, feel free to ask. I'm going fast. Okay.
Thank you for the presentation. It was great.
Okay, thank you.
Okay, so about crosstalk. So crosstalk is ideal specific error.
Especially
Error due to same frequency.
yeah. Right. Okay.
So only on Supercom.
Yeah, I think so, right? Yeah, like I don't know about other architectures, but it's like it's characteristics of a superconducting device, right? So yeah, when you apply two qubit gates at the same time, so like the way you apply two qubit gate is you put those two qubits in resonance of the same frequency, and like, but if you're applying another two qubit gate and there's some sort of frequency collision, there will be interaction between those two systems. So it creates to another error. So like that is crosstalk, and it happens like it's more significant when you apply those two qubit gates when they are close to each other in the connectivity, at least one hop distance. That's it. So here they try to like avoid this kind of parallel operation. Any other question?
Hi, Eyuel. So can I ask you one question?
Yeah, that's cool.
So in the previous slides, you mentioned like a software, like a scheduling software.
Oh yeah, here.
Yeah.
Okay.
So can we use this kind of software when we're using some like quantum computing cloud services like IBM Q or something like that?
Yeah, actually, this paper, they have implemented this scheduling module, and I think they also used it in IBM Q. Maybe like it could be, yeah, it's possible to use it in cloud service. I think they've implemented this module and kind of maybe it's, I don't know if it's integrated in the IBM Q's transpiler. But yeah, like maybe the transpiler also could use this kind of scheduling when you're running some quantum programs.
Okay, thank you.
So like if you transpile, you can select the optimization level option.
Yeah, optimization level option. So
it's, you don't know it's encrypted with that.
yeah, maybe like in the paper, I think they said like maybe it's already if they, I'm not sure if they contributed to IBM or not, but like in the optimization, if you increase the optimization level in transpiler, like skit transpiler, there's like it also analyzes some of its what do you call the qubit error rates, right? Like to give a better performance. Although it takes some time. Maybe yeah, it could be. I'm not sure of like the detail of the method used in the IBMQ's transpiler, but if it's not included there, maybe it's possible to use this module to run your quantum program on actual hardware. But the problem, like you might need some data of characterization of the crosstalk. So I think that is also done by like them in this paper, so it won't be a problem, I guess.
Also, who wrote this paper?
Okay, let me. It's here. Like actually in the paper. I think it's this one, right? Like they have actually have a link for their module. I think you can, yeah, I think, yeah, they like it's, I think they've provided the module for like crosstalk adaptive scheduler. So I think it's possible to use it, even though it's not integrated in the IBM.
But you have to measure.
Yeah, I guess they might also have like the module for characterizing the crosstalks, but that could take some time because you need to get data about like for several calibrations. So maybe.
I think Professor has paper
Okay.
about, sorry.
What?
I'm not sure, but I think Professor Bay has some paper related to crosstalk.
Oh, really? Okay. Is it some like using some sort of like algorithmic technique or just it's like compiling the programs or?
Yeah, I'm not sure. I think it was mainly observing that crosstalk.
Okay.
So crosstalk exists.
Okay. Maybe interesting to look.
Any other questions? If not, actually, I have one more question.
Okay.
So if you go to the first paper.
Okay, yeah, sure. Oh, okay. here? You mean this the variable like the first one?
Yeah.
Okay. This one is like a bit of an old one. It's not like it's 2018 something. Maybe the method is kind of outdated.
I mean, I was curious about what's the like why is called variational?
Okay, variability aware policy.
Yeah, if you
Okay. Which slide do you want?
no, can you
Back,
like forward.
forward? Here.
Yeah,
Okay.
maybe one for one more.
I think this is the last one.
Yeah. So PQ.
PQM is yeah. So this
Yeah, I thought that baseline is finding shortest path.
yeah,
Relative
yeah,
shortest
just like minimizing this number of swaps. Yeah.
minimizing the number of swaps or minimizing the weighted.
That one is the variation, the VQM.
So why is called variation?
So
Just weighted.
yeah, like it's called variational because like if you have some sort of qubit linking, like you have a different link, but without you can assume that like all links are like uniform. So you don't like even consider the variation of this qubit link strings. So at that point, you want you want to minimize the total number of swap gates. But if you consider the variation of this link, you might like want to go a longer path of swap gates, but it gives you a better like, probability of success.
I thought variational is it PQ.
Oh, okay. No. It just considers like the strings of the link, or like they're different. Yeah, that's why the name is called like not all qubits are created equal. Like there's difference in the like, performance of each qubits.
That's also a property of superconducting qubits, right?
Yeah. It's I think it's one of their properties. Since you have like fixed qubit frequency and after I'm not like sure about the like, it's like experimental meanings, but they kind of you know, have like some sort of variation in after that like after since you determine them like you need calibration every time, right? Yeah, that's also one.
Okay, so if you guys don't have any questions, no questions in June. So thank you for your presentation and let's end this meeting.
Okay, thanks for coming.